Hey, yeah, so we're going to be going over section 7.9, um, which is, it's titled Lagrange's equations for magnetic force. And basically what magnetic force, the problem that it does, that is why we have to look at it separately, is, hey, he's my puppy, but the force, the Lagrange of it does not equal kinetic energy minus potential energy. So this whole section is over like, what do we do with that then? Um, so let's get started. I'm gonna try and make this as quick and painless as possible. But it was a little bit of a weird section. Okay. So the first thing this section does is it looks at so it takes the Euler-Lagrange definition that we have, which is right here in green, and that's what we're going to call the general definition of the Lagrange, which is true. And even in the form of this magnetic force, that holds true. And then what we're going to do from there is we're going to come up with a whole new definition. Now, our new definition is going to be a bit more general, um, but the old definition will hold true for it. So a bit more on that is if this is the Lagrange's general definition, then what we're going to do to create a new definition of Lagrange is we're going to take a function of f that is a function of x and x dot, but they're inseparable. So some function like maybe x times x dot down here. And we're going to apply the same thing as we have in Euler-Lagrange's equation to that function of f. And then what we're going to call our new Lagrange function is our old Lagrange function plus the f function. So whatever is giving us problems with it, we just take that part and add it into what we call our new Lagrange. So here's the part that works out nicely and is t minus u, and here's all the extra change. That's all that first part really does. And so now we're going to go for an example of it and see. Okay, so we're going to start with a Lagrangian for a charge. Actually, we're going to start and finish with this. For the charge part, for a charge in a magnetic field. So the first thing the book does is it's just going to tell us right off the bat that what Lorenz's force is. So that's going to be the force experienced. And it'll be equal to the charge times the electric field plus the gradient of the cross product between the gradient and the magnetic field. So that part the book just gives us, and we can say that we know that the force is gonna be equal to m times some r vector time derivative taken twice. So from there, what the book points out is our new goal is that we want to be able to spot our Lagrange. So we're kind of just going to manipulate it until it's a little bit easier to see. So yeah, the book has us do this. What it's doing is we're going to take two equations, and we're going to redefine this electric field and the magnetic field. So I'm going to use these in purple, and I'm going to tell you right now, these come back at the very end. So these are important ones to kind of like remember. They just come back to take an ugly answer and make it look pretty. Because they're about to take this pretty answer and make it look ugly. So basically, the textbook is telling us to use two arbitrary vectors, like use scalar vector potentials is what it says word per word. So here's what it redefines these two as. It says that the electric field is going to be the gradient of some b vector that is, it relies on r and t minus this a of, so minus an a vector over the time. And so b is going to be a little bit simpler, where it's just going to be the gradient cross of with a. So I'm going to write down what those are. So v is a function of r, t. The book really doesn't explain explicitly what they are, but I'm going to be under the assumption that these are volts, like voltage and current. Just why wouldn't it be? But yeah, so that's what the book gives us. The purple's gonna come back, so we want to remember it. And this too, you'll see this again, but not full. It's gonna be interesting. Anyway, we're gonna take that and we're gonna plug these into this green equation. And at the exact same time, we're going to take the Lagrange. So I'm going to do that to make this video shorter. But if you don't want to do it all in one step, I'd say put these in and then take its Lagrange. But we're just gonna go for it. So the Lagrange that we end up getting is going to be L of R dot, and T. So when we make this Lagrange, we're going to make the assumption that it's going to work beautifully using kinetic energy minus potential energy. So we're going to say 1/2 m r dot minus q times v minus r dot dotted with that a vector. Okay. My dog knocks on doors a lot. So if you hear knocking and slash scratching, that's what that's going to be. Anyways, that's what we start off with. And then, so this potential that we got is from this force. We take the gradient of that and we end up getting this. And then the next thing to do is we're going to break it apart. So 1/2 m times x dot squared plus y dot squared plus z dot squared. All right, break it apart even more. Hopefully there's going to be enough room. All right, we get b minus, so v is going to be more of a constant, x dot a in the x direction. And I'm going to scoot it over so we can write it out fully. And then we're going to get minus y dot y minus z dot a in the z direction. Okay, so basically that a is a lot more of a vector, and the v is going to be continuous, like it's going to be constant in each direction. So it's a scalar. So we can just leave that alone. It's nice when the book does that for us. Yeah, so I'm going to zoom out actually a little bit so we can get the whole picture. Great. So that's our equation that we're working with. And then what we're going to do from there is we're going to run a check on it. And how we're going to do that is we're going to take the Euler-Lagrange equation that we love so much and have so much faith in, and we're going to do that. We're going to do it only in the x direction because it's going to look exactly the same in every direction. So we're not going to do the same thing 3 times. Okay, when we do that, here's what we end up getting. So the derivative of the Lagrange with respect to x is going to be gross. Here's what it's going to be left with. Negative q minus whatever that v is, its derivative with respect to x. So that's reliant on x, so we have to carry that with us. So x dot isn't reliant on x, but a sub x is. So we're writing it like that again. So basically taking this v, all these a's, and just knowing that they're reliant on x, and we can't fully show that, but we're going to carry it along with us. So we'll do that for the rest. Okay, so that's the first side. And now the second side is going to be the derivative with respect to x dot. So, and then we're going to take the time derivative of that. So I'm going to write time derivative of it. So when we take the first derivative with respect to x dot, we get x dot minus or plus q a x. All right. And from there we can take it again. We'll just, what we know from it is that x dot dot plus, I guess that's a constant, so, oh no, because that's going to be still reliant on it. Q a x, and its derivative with respect to time. Yeah, that's what's going to be left over there. So it's pretty, isn't it? Yeah, so what it's having us do from there is it actually wants us to break apart this last part that we have right here even more. So I'm going to write it all out kind of again, but I'm going to move this over here so we have enough room to see it. So it's going to be equal to mx dot dot. So the reason we do this is it's more of a chain rule because this a is a vector. So we want to treat it as such. So we end up getting this. Come on. Actually, I think this is going to be more accurate than this one. I'm going to be really honest with you. I think that was not my most accurate work. This will be. Okay. X dot derivative ax. Okay. So we ended up doing this for some reason because it's reliant on t and each vector is reliant on t. So it's just, it gets ugly fast. Yeah, that's all I can tell you about that is it's just quick and ugly. So what we're going to do now is we're going to combine this and this, and I'm going to solve for this m double time derivative of x. When I do that, I'm just going to put them all on one line so it's a lot kinder to read. yeah, so this second yellow equation that I have highlighted, I'm going to go back over it in green. But we ended up with that because we had to respect a chain rule. So we had to take its time derivative, but we also had to take its derivative with respect to each vector that it already had. So that's why that was produced, just as a more clear reasoning. All right. Great, so that's what we end up getting. When we factor it all out, rearrange it, you're gonna get something very pretty like that. It's not gorgeous, but it's okay. It's okay looking. So what we're gonna do from there is we're gonna use our definitions, I'm just going to scroll you back up, of these purple equations, just to make it look exactly like that. So each one has a gradient in it, and what we have down there, it takes gradients into account. So I'm gonna give you all the nicer version of it. So what it ends up looking like when you plug those all back in is you get this. Which is, it looks a lot like the force that we had to begin with in the first place. So that's very nice. And that's as far as the textbook takes this. And it goes out to explain that it is equivalent to what you get using Newton's first law. So that's always nice to know. But then it wanted to make a stronger point than that. So it said the most important thing we can get from that is actually right here. So this part right here. So that is going to be our momentum in the x direction. So I'm going to take it back down here and write it again, just so we don't have to deal with clutter. So that momentum in the x direction is going to be equal to just the derivative of the Lagrange with respect to x dot, which would be this that we had up there. And the reason the book wants to point it out is it gets special when we turn it into generalized momentum. So the generalized momentum, which I'm just going to write as P, is going to be equal to the mass times the velocity plus the charge times that a vector, which it now names this a vector as a magnetic term. And it says that it doesn't even go much further. It says that this is the result at the heart of quantum theory in a charged particle and magnetic field. So that's all this chapter goes over. It does not go into that quantum theory. It just wants you to produce this and know that this is the momentum you get in a magnetic field, and show you how the Lagrange works in a magnetic field. From there, that's all in this section. So I'm gonna put the link to the notes in the comment section below. If you have any, or the description section below, if you have any questions, put them in the comment section.